Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Susheel Tadikonda, who's going to talk today about some of the issues in building and designing an AI SoC. Susheel, there's been a lot of activity going on in the AI space. Obviously, people have been building chips out of GPUs, CPUs, almost everything, but a lot of that has been very customized. What do we have to do in order to get the same kind of economies of scale we've seen in other designs instead of having 100 companies trying to develop chips that are 100 times faster?
That's a big problem, actually, which a lot of the big companies, especially companies like ARM or any of those traditional architecture companies, they're facing, right? Because if you look at the AI silicon, it's not just about people looked at CPUs, GPUs, and now the problems moved a lot more from a data center towards the edge. So that's why people are pushing into more of the custom logic to do it, okay? Because there is no standard architecture per se today, okay? So people are implementing, everybody's trying to solve the same problem. If I take an image, I get an image, and how fast can I process the image? And how many images can I do at the same time? People are coming up with their own different architectures to do this. There is no standard architecture. Which one of this will succeed? We will see. I mean, you have seen TPUs, which are already used by Google with a certain architecture. That's been pretty successful. Now Amazon's come into the play. Now Facebook's coming into the play. So each one will have their own architectures. But at some point, we'll see as to how they all converge into one standard ISA.
Because these things are so customized, do the tools that exist today and the methodologies, do they work for building those kinds of chips the same as they have in the past for other complex SoCs?
Okay, so you need to first understand that in the AI problem, the AI SoC's problem is not an RTL problem. Okay, and I'll explain that a bit more in detail. But if you look at the chips by themselves, they're very simple chips, in my opinion. The complexity is in the whole compiler and the runtime software, along with the chip architecture itself. So if you are looking at traditional verification methods for these chips, it's straightforward because they're all replicated, repetitive entities of the same elements. In this case, ALUs. We're just trying to repeat all of them. Verifying those is very easy. But verifying them in the context of the upper layers, which is the compiler and runtime software, that's the hard problem.
Why don't you draw this out for us?
Sure.
What are we looking at here?
Okay, so before I start talking about a bit more on the AI SoC complex and stuff, I thought I'll at least give a little bit of a context, right? So if you look today, neural networks, which is the number of algorithms that are out there, are just growing far and few. Every day you have gobs and gobs of new algorithms being pushed out, new models as to how to implement these are coming out. Okay, people have started to say, you know what, these algorithms exist. How do I implement these algorithms? And they've started looking at different architectures. So people originally started looking at CPU because AI chips, if you understand, are nothing but a math problem. You're trying to do a lot of math inside. So people said, okay, let's do CPUs because there is a lot of math inside, and then do it. But CPUs have their own latencies inside because of the cache misses and blah, blah, which may not lend itself well. Then people said, we have GPUs which have so many floating point units, let's use it. So GPU in my mind was an accidental find for doing SoC or AI SoCs. The GPUs play, don't get me wrong, they play a big role in the whole learning in the data center. And people after that, since the problem now is moving a lot from data centers to more on the edge devices, people have started looking at different architectures. So you have FPGA based and also custom logic. All of them trying to do the same thing. They're all trying to solve that problem of you have so much of workload to process at low latency and low power.
Where do FPGAs and some of the more specialized, like the tensor processing unit, where do they fit in?
Yeah, okay. As I said, the GPUs, they are your standard GPUs. There's nothing specific being done for solving your AI kind of problem. They inherently do it because they're a bunch of floating point elements. FPGAs and the custom logic, in the case of whether it's a TPU from Google or the Wave or any of the Facebooks or Amazons of the world, right? Everybody's trying to come up with their own architecture because each one has a different workload problems to solve. Okay, one thing we need to understand is that each of these companies have different algorithm implementations and different workloads. So everybody is trying to cater some architecture to their own workload to solve it in the best possible way. So at this point, the generic implementation of just a CPU and GPU is not cutting for these people. So they said, okay, fine, I have an FPGA. FPGA also, because remember, AI chips are nothing but it's a layering of processing elements. You get some image, let's say, and you have a bunch of processing elements. You're taking it down the long path of it to process, and each stage is being processed. So FPGAs lend itself well. There's one camp which says that. There's the other camp which says we don't believe in FPGAs. We got to do our own custom logic, which is where the TPUs and the IPUs of the world are coming in.
And one of the problems with the whole ASIC approach, which is the TPU and IPU, is that there isn't enough volume because these things are changing so fast. Everybody's worried that if they build a chip, it's going to change and they won't have the kind of economies of scale, right?
That's the reality, okay? Algorithms are changing. I mean, I've never seen something change so fast where what you have built may not be valid by the time it actually comes out into the production. I mean, you're faced with that kind of a problem. So people are trying to come up with architectures which satisfy and solve a lot of benchmarks, so they can use it in different kind of workloads and stuff to solve it. But even like TPUs and stuff that you see, they've gone through generations. So there's first one, people come up, you learn a lot, and you try to build the next one, you try to become much better at it, and that's the trend that you will see. Chips have to be one key thing in AI. You don't have the luxury of a long cycle time to build a chip. It has to, from concept to production, it has to be fast. Because the world of the algorithms is changing so fast, you got to be able to build and develop that quicker.
So in the midst of all this change and churn in the algorithms, there's got to be some commonalities, and here are things that you can build in, right?
Okay. You have images coming in, you have to process the image, right? And you have to process many of those images in a much shorter latency. So basic thing is that you need an architecture which has a powerful compute element inside. You need an architecture where you have a very good memory architecture where data can be supplied to these compute elements at a faster rate. Okay, and since all of this stuff have to go to the edge, power plays a big role in this, right? So if you look at the commonalities, you have compute elements, you have a great memory architecture, right? Power is always a concern, and then you have I/O traffic, in the sense there is always an interface, whether it's PCIe or AMBA or whatever. Those are the commonalities. Where they digress is the implementation aspect of it. Some prefer vector processing, some prefer FPGAs, some prefer traditional ways of doing it, right, with memories and caches and stuff like that.
But from the standpoint of a design, this is problems we're very familiar with, right? Because we've been dealing with low power for a number of years, ever since we've got below 40 nanometers. We've certainly been dealing with the I/O issues of moving data through a chip.
Low power problem is there. No matter a lot of chips that you look at, low power is always there. And because these guys are churning so much of data processing, power definitely plays a role. What's pushing it is because these AI chips are making it to the edge, power is taking a much bigger role because you've got to be low powered if you're on your phone.
So how does this diagram fit together?
If you're building an SoC, AI SoC, what are the things that are taken into account that go into building that SoC? Algorithm aspect is there. The algorithm is always changing and stuff. But what do you take into account when you're building it? The first thing is the data flow. Because you get an image and it has to flow through a pipeline of processing elements and the shortest possible path and to get you out. So that's the data flow as to what kind of, and this data flow could involve, for example, it could involve floating point registers, floating point units or integer units based on the kind of architectures that we have. The second thing is that latency. For example, if I have an AI chip I'm building for an automotive car, and moment I get an image, I better process it quickly. So that's where the latency is very important, the turnaround time of it. And second thing is performance. Performance in the sense, the same thing. If I take an automotive car, that chip has to process so many images. It's not just you, it's looking at the environment, the traffic lights, the trees. So it has to process a lot of data in a much shorter period of time. And all of it underneath is low power. So these are the four elements, and there needs to be a balance among all these four elements for you to build a chip.
And the balance changes depending upon what you're trying to do in each different application, right?
It could be. For example, let's say if I am putting this stuff into the data center, my power envelope is a little bit bigger than what I have in an edge. So you can make some compromises on that to give a boost to the other side of it. Okay, the other side, for example, if I'm building an AI chip for an automotive car, it doesn't have to be precise. For example, it just needs to know that there's a human being or something there. It doesn't exactly need to know this is this person. You understand? So the precision aspect could change. So that's a compromise that you can have based on the kind of chips that you have.
Are we ever going to get to the point where these chips are going to be fairly easy to build and modify as we go forward, almost a modular type of approach?
I would say yes. That's the way the push is happening. Because as I said, remember, these chips are not difficult to build. These are just elements, bunch of processing elements tied together, right? What is the hard part in all these chips is the software that runs on this one, and that's the picture that I'm trying to draw here. You have all of these elements. It's a balance between these to build your SoC, but because you have a custom architecture, you have a custom compiler because the compiler understands your underlying design. And then there's a runtime scheduler that goes with it because this scheduler is the one which is laying out all your weights and stuff based on how your architecture is implemented.
Right.
And then on the top of it, you have all the frameworks and the models that you talk with. So the complexity here is, yes, I'm building a piece of silicon following this one, but will it perform to the spec with this kind of infrastructure under the workloads that you were supposed to be qualified against? So that's the challenge.
It's an interesting balancing act.
It is a big time balancing act.
Susheel Tadikonda, thanks for a great explanation.